So yeah, let's continue. So we studied about alpha scattering, we studied about linear accelerators, and we also studied a little bit about relativistic effects of particles on particles when they travel close to the speed of light. So the last thing we said was that linear accelerators were good, but they're not good enough, because they have a limit to how much they can feasibly accelerate particles to. So the largest accelerators we have, or the largest one there is a standard linear accelerator, which accelerates up to 25 giga electron volts, right? Which sounds like a lot of energy, but that doesn't necessarily mean that that's like, the highest that we can go. We can actually go faster. So yeah, now let's talk about cyclotrons. So how do cyclotrons basically work? What they do is they use the same concept as linear accelerators. Linear accelerator acceleration ta koi hoychilo? It happened between the gaps, right?
Yeah.
So ekhane amra particle dislam, acceleration occurred between the gaps when this happened. Now cyclotrons kore ki ekhane amader limitation chilo the tubes become longer and longer. So the cyclotron solves this issue by not even using any sort of linear accelerator. It actually accelerates in the form of a circle, or actually a spiral. Basic concept ekটু bojo, tarpore you'll be able to understand. So first of all, how do we bend a charged particle while accelerating it? So what we need is basically a magnetic field. Alright, so we take a magnetic field, say, and then what we do is we can introduce, say, a charged particle into the magnetic field. So say we take a proton, right? At a vector velocity te she magnetic field enter korlo. Now we can use this to actually figure out the direction in which it would bend, right? Ki korba? You use the left hand rule. Left hand rule can use korba because here you're having a current flow and you have a magnetic field. The current flow is the motion of the positive charge. It is the negative hoito current flow kondike hoito ulta dike, right? It would be to the left, but here the current flow will be to the right. Does this make sense?
Yeah.
All right. Tarpore jeta kora hobe is that a particle it would accelerate and enter the magnetic field, and the crosses mean what? The magnetic field is into the board, right? So এখন আমরা যদি left hand rule use করি, so force by করতে হবে, which is our thumb, right? Field কোন দিকে হবে? Into the board. Our current is going to be to the right. So as a result, what do we see? According to the left hand rule, current এদিকে, আর this is a field into the board. So the result is going to be a force upwards. Force, field, and current. So this will basically bend up. Another important জিনিস আছে. This motion is not parabolic. It's actually circular. How do we know this? Because the force will always be perpendicular to the direction of motion. So এখানে ছিল force is vertically upwards, এখানে একটু bend করবে, আবার এখানে যদি আমরা আরেকটু curve করি তাহলে কোন দিকে হবে? আবার tangent রাখলে it's going to be a direction, right? So you're seeing what's happening. What's happening is basically the path of the particle is following a circular path, circular pattern. And the reason is because the force, the magnetic field, is actually creating what we know as a centripetal force, right? It's a centripetal force which is pulling it towards the center of the circle. So if the magnetic field is large enough, then technically, say we take a large magnetic field, and if I'm like the charged particle name, then we can technically accelerate it and then make it go around in a circle, right? Usually, erokom circle constantly at the speed rakha jay na, because as this charge is also accelerating, because circular motion is going to lose energy in the form of electromagnetic radiation. Okay, sir. So etar karone what we have to do is, even if we want to keep it at a constant velocity, or the constant now, we want to accelerate it, we need to accelerate it somehow while keeping it in the magnetic field. Alright, what's going to happen if you accelerate it? That's the next thing that we have to understand. Ekhane ki force act korbe? Ekhane basically we have two forces, right? Actually this is magnetic field eta, and this is central force. So magnetic field force amra kemne bar kori? F is equal to BQV, right? And another one is F, if we take central force, F is equal to mv squared by r, right? So we can equate these where mv squared by r is equal to bqv, right? এখানে অবশ্যই একটা sin theta থাকার কথা, but এখানে আমরা assume করে নিতেছি that this is happening along this flat surface. So the field lines are perpendicular to the direction of the current flow or the motion of the charged particle along this. And this is a horizontal plane and that's a vertical plane. So যেটার কারণে we don't even have to mention the BQV, the sin theta. So এটা simplify করলে কি আসে? If you simplify this, you end up getting R is equal to mv by bq. ঠিক আছে? If we simplify it, কাটাকাটি করে তুমি দেখো যে এটা আসে, bv এর সাথে কাটলা, R এখানে নিলা, bq নিচে চলে আসলো. So mv by bq. So what does this say? This says the radius of the path is proportional to the momentum ঠিক আছে, mv. So the faster the particle is going to move, তত obviously your momentum বাড়বে. Momentum বাড়লে কি হবে? আস্তে আস্তে it will begin to spiral with a greater and greater radius. ঠিক আছে? So this is all right. As long as আমাদের magnetটা we can make it large enough, we can actually keep it and accelerate it, right? So we've kind of got everything sorted out except for how to accelerate it. And arekta problem হইতেছে যে we can't really build big magnets. ঠিক আছে? If we make magnets which are more than like 1.5 meters diameter, then the magnet starts becoming too weak, and the amount of current needed to actually hold it together is no longer efficient, or it's not feasible. So usually the largest cyclotrons we have are like 1 or 1.5 meters in diameter. So now that sorts out how we're going to do it. And accelerate korle she just spiral out korte korte ekta point e giye what we can do is we can keep a small gap je ekta certain yete giye it accelerates out of the field at a high speed, which is nice. It's all working nice and fine. Now the problem is, how do we accelerate it? We're still stuck with this problem. So one way of accelerating the charged particles is what we can do is, say we take a charged particle, say this is a charged particle, and we place it between two semicircular Ds. These are hollow metal Ds, and with this we charge them up. So one is positive, one is negative. So what will happen to this charged particle? If this is positively charged, it's going to move into the negative D, right? All of this is inside a vacuum. And also, all of this is placed in a magnetic field. Oops, not like that. Like this. So this represents the field is entering or passing through the metal Ds. Does this make sense, guys?
Yes.
Alright, so more or less. So how would this help? If you look closely, what would happen is, if we again apply Fleming's left-hand rule, the charged particle will accelerate and then it's going to curve up. So it curves up and then it would exit the D on the right side, and then it accelerates between the gap. Keep this in mind, acceleration between the tubes. The acceleration is going to happen between the gap. The system again has to be smart enough to alternate the polarity. So if this is positive, ঢোকার আগ পর্যন্ত এটাকে নেগেটিভ করা হলো, এটাকে পজিটিভ করা হলো। এটা যখন ঘুরে এদিক থেকে অ্যাক্সেলারেট করে এদিকে বের হবে, তখন by the time this comes out, this will be made positive, this will be made negative, so it accelerates over the gap. এখানে এসে, so it's going to accelerate here, right? So if it accelerates, what does that mean? The momentum is going to increase, so the radius is going to increase. So it's going to start creating a spiral of larger radius, a circle of large radius. So you might ask, acha তাহলে তো এখানেও frequency change করতে হবে কেন? Because এখানে it's covering a smaller circle arc, আর এখানে it's covering a larger circle arc, right? So এখানে এসে what actually happens, this is the smart part about cyclotrons, the frequency remains the same কেন? Because or speed বাড়তেছে ঠিকই, but also the radius of the arc that it covers ওইটাও বাড়তেছে.
So they're traveling a high distance.
They're covering a greater distance. So basically the frequency at which this alternates can be kept constant. Do you get it?
Yep.
So abar ekhane cross korlo abar larger radius বুঝছো? So erom kore, so if we were to simply show it, তাহলে আস্তে আস্তে as it speeds up, the spiral increases. And then একটা point ধরো, you can allow it to exit from between the Ds. Is this clear? আচ্ছা. So এখন basically this is how we ensure that the frequency doesn't need to be changed, because that's how we can actually make it very easy to operate. So this is the basic concept of a cyclotron. Cyclotron, bujar shomoy, students sometimes it's hard to visualize this. So what we've done is basically we have this nice design that we've put together, which is supposed to represent a cyclotron. Not exactly the best design on earth, but basically, yeah. So first of all, this would be the chamber within which we're holding the entire cyclotron, right? So this would be the vacuum. The interior of this should be a vacuum, or at the least it has to be inside here. So yeah. Let's remove this. This is just a software that we use for 3D designing and everything. It's called Tinkercad. So I'm just using it to show you guys exactly how.
Are they sponsoring this video?
No, not really.
Yeah.
I'm just showing it. It's free and it's nice. If Tinkercad calls me, then I'll let you know. So yeah, now these two, the blue and the red pieces represent the poles of the magnet. Alright, so one of them is obviously a north pole, another is a south pole, but obviously you don't get them unipolar. Basically the other side is going to be a south pole, so they complete an entire magnetic field. Alright, so anyway, to simplify things, let's remove one of these. So here we have this nice cute little charged particle sitting right there. So this would be the gap in which the charged particle actually gets accelerated. Alright, and the inside of the Ds are hollow. So basically, if we were to show the inside of one of these, let's see, we can use this to show it as a hollow. So this is what it would look on the inside. So what would happen is basically the particle would enter here, accelerate, and then come out the other end at high speed. So does this make sense to everyone?
Yeah.
Alright, so it's pretty much very straightforward and not anything too complex. So say both of these are hollow Ds, and here we have the charged particle. So how would it become? It would basically accelerate, right? What would happen is it accelerates between these. These are the two Ds that we actually charge up. We make one of them positively charged, we make another one of them negatively charged, right? And the acceleration happens within the gap. And then they accelerate, they enter, they move at a constant radius inside the D because there's no field, right? Remember that? And then it accelerates across the gap again, then accelerates, and then moves with a greater radius. And then keeps doing that until it accelerates, and then at one point, but we could, that it would basically exit when it gets out of the field, or when it becomes too large for the magnetic field to actually hold it together. Is this making sense?
Yeah.
So I guess fair enough, the concept is clear about how this works, right? Alright, so yeah, that's the basic concept of a cyclotron. Now, there's a little bit of maths related to the cyclotron's behavior. Alright, the first thing we need to know is we need to figure out at what frequency does a cyclotron accelerate. So for that, what we can do is we can use a very simple set of formulas. Frequency is equal to 1 by time period. You guys know that already. And for this, as this is moving along a circular path, we could say the time period, or spiral, time period is equal to what? 2 pi r, basically the circumference divided by the speed of the particle. Does this make sense?
Yeah.
Alright, so we can get an idea of what we're trying to do, right? We're trying to figure out the frequency at which is we'll have to alternate it, right? To cover the field every time. And also, we know that radius, our vector formula, which is written right here, r is equal to mv by pq. So I won't go into the trouble of deriving too much of this. I'll just write this in two sentences, two lines very simply. T is equal to 2 pi mv by dqv, and this can be written as 2 pi m by pq. Do you get it? So the frequency of the cyclotron is going to be the inverse of this, correct? So it's going to be bq divided by 2 pi m. Does this make sense, guys?
Yes.
Ashalo?
Yes.
সত্যি নাকি হ্যাঁ বলতেছো তোমার তো আবার দুই স্টেপ মিস করলে তোমাদের মাথা নষ্ট হয়ে যায় ইকুয়েশন কই গেল পার্টিকেল কই গেল স্মার্ট আছো লল যাই হোক anyway so frequency cyclotron frequency is bq by 2 pi m. This is এখন we have to go back to what we studied একটু আগে, the concept of relativity and relativistic effects. Now the cyclotron frequency remains as this if you're accelerating it to really low speeds, right? Not even anywhere near even a small percentage of this frequency, the speed of light. So on here, this sort of stuff works. But what's going to happen when we're going to start accelerating it at relativistic speeds, right? The mass is going to start increasing, right? What we saw in relativistic effects. We can no longer use this equation. At relativistic effects, we'll have to consider the effect of relativity. So we'll have to multiply this with root over 1 minus v square by c square, right? This is basically now synchronized with the change in mass, right, of the cyclotron's acceleration of the particles. So if it's just a cyclotron with no effect of relativity, then we could just say bq by 2 pi m. And the moment we bring in relativistic effects to synchronize it with the effects of relativity, we say bq by 2 pi m, same equation, but we multiply it with root over 1 minus v square by c square. This equation is also known as the synchrotron equation. Do you know why it's called a synchrotron? It's pretty obvious now.
Because it syncs the frequency.
It's synchronized. It's a cyclotron which is synchronized with relativity, right? Or the basic change in mass. Because therefore, mass bale ki hobe, frequency kome jabe. So what's going to happen is at higher and higher speed, as you accelerate this particle more and more, v value to the power, the frequency at which it's going to operate is going to decrease. So we can't operate it at the same frequency because mass is more, right? So we have to treat this as a synchronized cyclotron. So the full name would be a syncocyclotron, but we don't call it a syncocyclotron, we just call it a synchrotron. Does this make sense?
No.
Alright, so this is now going to allow us to talk about one of the most advanced accelerators we have, which are known as the ring colliders. Have you heard of ring colliders?
No.
Achha. Ring colliders are basically an advanced version of cyclotrons. Cyclotron আমরা কি করছিলাম? We had two hollow metal Ds, আস্তে আস্তে বাড়ছে, তারপরে সে বের হয়ে গেল। What if, and this was based on the equation R is equal to mv by v cube, right? So basically what happened, momentum যত বাড়ছে তত আমরা radius বাড়তেই হয়েছে। What if we did something else? What if we actually gradually increase the strength of the magnetic field as the momentum increased? তখন কি হতো? তখন what would you see happen?
Radius is constant.
Yes, very good. তখন what you would see is basically তোমার a ring collider, না, cyclotron মধ্যে it would basically be accelerated over the same radius constantly, right? So যত radius, যত momentum
So I
বাড়তো,
need less space basically.
yeah, you don't need any of this, you don't need any of this, কিছুই লাগতো না, right? So this is what we could do. So this is the concept of the ring collider. And ring colliders are obviously also called synchrotrons because basically they use the concept of cyclotrons and also they accelerate particles to really high speeds, alright? So synchrotrons, like, they can accelerate up to like, even the simplest of synchrotrons, they can accelerate up to 1 tera electron volt, which is like really, really high compared to the giga electron volts that one linear accelerator can do, right? So we use this. So how is it that we can actually construct this into one basic ring where you don't really need any other matter? You can just accelerate it over this ring and just ensure that the charge, the magnetic field strength accelerates. The magnetic field strength increases as the particle accelerates and gains momentum, right? This is the entire concept of the Large Hadron Collider, which is also known as the ring collider, right? And we'll be talking about that next. That took it clear?
Yes.
Alright, so yeah, what did we do? We basically talked about the concept of the cyclotron, right? How basically we have relativistic effects and how we have to consider that. That's the first thing. Then we talked about how linear accelerators are limited by the length of their tubes. Hence we go to cyclotrons. Cyclotrons limitation is also there. It's limited by how large the magnet can be, right? So then we figured out how we can bend a charged particle in a magnetic field and how we can use that to actually accelerate particles. And we also talked about a simple design of a cyclotron, which is basically this, where you have two metal Ds between two magnets, right? Duita magneter মাঝখানে দুইটা metal D রাখা হলো, and from that we can actually figure out that the particle is going to spiral as it accelerates. And then we talked about how we have to consider the effect of frequency. If we're talking about non-relativistic speeds, it's really simple. It's just v cubed by 2 pi m. And the moment we bring in relativity, we have to consider 1 minus v squared by c squared. And this is then called a synchronized cyclotron or a synchrotron. And we can use this concept if we can vary the magnetic field strength in a ring collider. And that is the concept of the Large Hadron Collider. Alright? So yeah, that's that.